Imagine a sprawling megastructure floating endlessly through space. One day, humans may occupy an orbital settlement several hundred kilometers from Earth. Perhaps humans will settle closer to the Moon or in the main asteroid belt beyond Mars. If humans ever migrate into space, what would our settlement look like, and how would we navigate life in the final frontier? A space colony must withstand the harsh conditions of space, but it must also create a safe and comfortable environment for generations of human colonists. Any habitat must have replenishable sources of food, water, breathable air, and medical supplies, and it must spin to produce artificial gravity. Though scientists are unsure how much gravity we need, space colonists also require protection from solar radiation. The sun releases a continuous stream of charged particles called solar and wind, and intermittently strikes in deadly bursts known as solar particle events. Further radiation from galactic cosmic rays and charged particles trapped in the Van Allen belts may endanger the occupants of any space colony. Scientists have overcome some of these hurdles while constructing the International Space Station, or in 1998, the first modular piece of the ESA's launched into Earth's orbit. Over the next 13 years, international astronauts and engineers pieced together a microgravity research laboratory, roughly 400 kilometers above the ISS orbits our planet. Every 90 minutes, flying about 28,000 kilometers per hour for more than 20 years. The ISS has safely accommodated teams of astronauts and remains the longest habitable space station ever constructed. The ISS is not a permanent self-sustaining habitat, nor does it provide a comfortable environment for scalable colonization. Astronauts occupy cramped corridors and survive on vacuum-packed or freeze-dried, isolated environment. Astronauts are susceptible to social and psychological problems like anxiety and depression. Prolonged exposure to weightlessness or microgravity also causes changes to the body's organ systems, including muscle atrophy, visual impairment, and a loss of bone density. Though the ISS is not a permanent settlement, it has yielded valuable insight into life. In free space, were humans to construct a larger structure, say for 100 or 1,000 colonists, we may build upon the technologies used aboard, for instance. Any space settlement must be equipped with a closed-loop life support system. The ISS's life support system is not a closed-loop system, but it is generations beyond the earliest days of spaceflight when astronauts carried all their oxygen and water in. Over the years, the ISA has served as a test platform for an environmental control and life support system, or ECLS, which recycles water, maintains temperature, and ventilates habitable cabins. Two devices generate oxygen by electrolyzing water, while carbon dioxide and other volatile gases are absorbed and vented into space. For the past few years, the European Space Agency has been testing a different life support system which processes roughly 50 of CO2 on the IS to create oxygen. Newer. Still, a photobioreactor built by German scientists uses photosynthetic algae to consume CO2 and release oxygen in the presence of life. This system also produces biomass, demonstrating how future life support systems could supply astronauts with replenishable food. Still, some oxygen must arrive from Earth in tanks, not only for emergency storage but also for use in. Currently, the EISA cannot pressurize generated oxygen to support astronauts on space. The station also relies on rare shipments of nitrogen, the most abundant gas in the cabin air. As future spaceflights like NASA's Project Artemis take astronauts farther into space life, support systems will advance. Incrementally new systems may generate an Earth-like cycle that provides breathable air and replenishable food for astronauts and eventually space colonists. If we design an efficient closed-loop system, how might scientists construct a habitat capable of supporting a large colony in free space? Scientists have attempted to answer that question for over 100 years, but many of the most influential ideas come from the mid-1970s at the time. An influential physicist named Gerard O'Neill believed humans had the technology to construct orbital cities capable of housing millions of people. In McNeil's first conceptual space colony feature huge cylinders about 32 kilometers long and 6 kilometers in diameter. Each cylinder encases a long strip of artificial terrain, yielding 1,300 square kilometers of living space. The O'Neill cylinder, as it is known today, creates artificial gravity by rotating on its axis. The outer shell has thick radiation shields and its walls are covered in solar windows, providing colonists with warmth and light incredibly. The O'Neill cylinder was designed to support a thriving natural ecosystem inside each cylinder. O'Neill imagined rivers, forests, and parks alongside cities and neighborhoods populated by over 1 million colonists. Another innovative megastructure was proposed in 1975 by a NASA summer study at Stanford University. Their conceptual model, known as the Stanford Torus, is a donut-shaped habitat with a hollow residential tube. A population of 10,000 colonists could occupy the tube's inner ring where cars and homes are held in place by the torus's rotational gravity. After the Stanford Torus, O'Neill proposed another habitat called the Bernal Sphere in this design. O'Neill downsized his massive cylinders to a globe less than 2 kilometers in diameter. On account of its smaller size, the Bernal Sphere rotates more quickly than a larger-scale colony, completing just over 1 rotation per minute to produce Earth normal gravity. These inventive habitats inspired many more concepts in the 21st century. In 2006, the Kalpana 1 orbital settlement was proposed as an improvement upon the megastructures from the 1970s. Kalpana 1 uses rotating cylinders like the O'Neill cylinder to create Earth's normal gravity caps. At the end of each cylinder, provide a continuous source of light and solar power, while shields in the whole structure protect colonists from radiation more. Recently, 2 scientists proposed a small rotating habitat that can launch directly from the surface of the Earth. One of those scientists also proposed an orbital settlement without radiation shields in an equatorial low Earth orbit, thereby reducing the settlement's total mass by over 95. Unfortunately, few organizations possess the resources to build or transport materials for a space colony, even a light or compact one. Thus, scientists have proposed innovative solutions to lower the cost of construction and transportation. If humans construct a colony near the moon, we could cheaply build structures out of lunar regolith raw materials launched from the moon to a construction site in free space could be assembled into walls, windows, and machines. Using 3D printing technology for colonies constructed in the main asteroid belt, humans could harvest resources from nearby asteroids and the dwarf planets. We may possess the technology to put a structure in space, but it's unlikely humans will create enough and replenishable habitat in the coming century. However, new hyper-efficient designs may accelerate humanity's push toward space colonization. Today, our society is largely bound to the Earth, but tomorrow our descendants may be living amongst the stars. Imagine a sprawling megastructure floating endlessly through space. One day, humans may occupy an orbital settlement several hundred kilometers from Earth. Perhaps humans